We just found an interesting rule for derivatives. We found the power rule, which says that if you have a variable to a power, taking the derivative with respect to that variable, that the power is going to come down, and you're going to get the variable to 1 power less. Now this allows us to skip working with that limit definition. We derive the rule based on the limit definition, but we can use it now that we know it. We don't have to go through all that work. We've proven it in a general case where n was some unspecified number, so we can apply it in any case where n is some specific number, like let's say 7. The power comes down and you get x to 1 power less. That saves a lot of time in terms of finding the derivative because you don't have to work with the limit definition. There are other rules that are very handy, and we just want to keep amassing these rules. You'll want to work on memorizing these rules because they'll be very, very handy in the future if you know these rules. Let's look at first the derivative of a constant. So I'm just going to use C here to stand for any constant. I want to take the derivative. Well, let's go to the limit definition. All right, the limit definition says you would take the function at x plus h minus the function at x and divide by h, and then take the limit as h tends to 0. Now in our case, the function is just this constant, so it doesn't matter what you put in, the output of the function is always going to be the same. It's a constant function, so that constant c will come out. So we'll have the limit as h tends to 0 of c minus c over h, which would be the limit as h tends to 0 of 0 over h, which should be the limit as h tends to 0. 0 divided by some non-zero number h is going to be 0, and the limit as h tends to 0 of 0, since that's the limit of a constant, that's just going to be 0. Okay, so this is another rule. Anytime you need to take the derivative of a constant, you're going to get 0. For example, if someone says, well, what's the derivative of 2? Well, since that isn't changing with x, it's going to be equal to 0. This, of course, fits your intuition, because if you looked at the graph of the function f of x equals 2, no matter what the x value was, the output's always going to be 2, so you would get a horizontal line, and of course the slope of a horizontal line, there is no rise, so rise over run is always equal to 0. So the derivative of any constant is 0. It doesn't matter which horizontal line it is, maybe one above there, maybe one below there, the slope is still the same. Okay, useful rule. The derivative of any constant is 0. Let's get some more rules. Here's our constant multiple rule. Suppose that you want to take the derivative of some constant times a function that you probably already know how to take the derivative of. Well, you could fall back on the definition of the derivative and consider this case in sort of the abstract situation where the constant isn't specified and the function isn't specified. Now, in this case, we're trying to take the derivative of this. If we give it x plus h, we're going to get the constant times f of x plus h minus the constant times f of x, if we give the function x, divided by h, right? This is just the definition of what the derivative of this would be. And we can see that there's a common c in both of these, so let me factor it out. So the limit is h tends to 0 of a constant times x plus h minus f of x all over h. But we already know from our work with limits and our limit laws that the limit of a constant times a function, the constant comes through limits. So from laws for limits, we have the limit as h tends to 0 of f of x plus h minus f of x all over h. And of course, this is the definition of the derivative of f with respect to x, right? Or let's see, f prime of x might be another way to write it if you wanted to use Newton's notation. Let's look at an example. We know that the derivative with respect to x of x to the 7th is 7x to the 6th. So what if somebody asks us, what's the derivative with respect to x of 3x to the 7th? Well, according to this rule that we've just found, when you take the derivative of a constant times a function, you get the constant times the derivative of that function. So if we want to take the derivative of a constant times x to the 7th, according to that rule, that would be the same as 3 times the derivative of x to the 7th. And we know that the derivative of x to the 7th is 7x to the 6th, because that's a simple power. Now 3 times 7 is 21, so we get 21x to the 6th as the answer. once you kind of see it, you'll get much better at it. If someone says, take the derivative of the square root of 2 times x to the 4th, you just go, all right, well, the 4 is going to come down and multiply the root 2, and then we'll have x to 1 power less. Done, right? So you won't bother to pull the constant through. You'll just think, oh, it's just going to be there. I'll multiply it by that power once it comes down. So just for speed, you'll do that. Okay. More rules. Sum and difference rule. So here's a rule. You can also easily prove it if you use the limit definition of the derivative. If you need to take the derivative of the sum of two functions, it'll work out if you just work with the properties of limits. That's the derivative of the first with respect to x plus the derivative of the second with respect to x. So basically this differentiation operator can just distribute over to those two functions. So that would be really handy if you needed to take the derivative of some polynomial. Someone said, well, take the derivative of x to the 4th plus 7x squared minus, well, let's just stop right there for a second. Okay, so according to this rule, if you want to take the derivative of the sum of these two functions, you can just take the individual derivatives. The derivative of x to the 4th is 4x cubed plus the derivative of the second. We have the 7 here, which is a constant, so the 2 will just come down and hit the constant. We'll have 14x. There's the derivative. Now, the same argument works if there's a minus sign here. So you could also show that if it was f of x minus g of x, it would just be the derivative of f minus the derivative of g when you take that derivative. So also notice that if it involves several functions, let's say you needed to find the derivative of 3x squared plus 5x cubed plus 4x to the 7th, then what you could do is just apply this rule. Say this is my first function, x squared plus 5x cubed, and this is my second function. So this is like f plus g in this case. We'll get the derivative of the first function plus the derivative of the second function. But of course the derivative of this sum would just be the derivative of the first function plus the derivative of the second function. And then we still have tagging along here the derivative of this 4x to the 7th here. So we just get, let's see, the 2 comes down, 2 times 3 is 6x to the 1, plus the 3 comes down, 3 times 5 is 15, x squared, and then when the 7 comes down, 4 times 7 is 28, x to the 6th. We've got our derivative. So if there are multiple terms, then you just take the derivative of each one of those terms that's added. So that's kind of handy. Even if there were 50 terms, right, you just take the derivative of each one and add them all up. So you can even mix pluses and minuses. So if it's some sum or difference, you'll just do the sum or difference of the derivatives there. Oh, very handy, particularly say for polynomials. That's a useful trick to have here. Okay. The next rule is a little bit interesting. If you need to take the derivative of the product of two functions, it's not like limits, right? The limit of the product is the product of the limits, but we're talking about derivatives, which are a special limit that you apply to the function after doing this procedure of evaluating x plus h and subtracting x and dividing by h. So it's based on limits, but it doesn't necessarily follow the limit rules. In this case, it turns out that what the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. Let's look at an example. Suppose we need to take the derivative with respect to x of x squared plus 1 times x cubed minus x. So we want to take that derivative. According to this product rule, we would have the derivative of the first, so the derivative of x squared plus 1 is 2x plus 0, because the derivative of a constant is 0. So the derivative of the first times the second, which is x cubed minus x, plus the first, that's x squared plus 1, times the derivative of the second. The derivative of x cubed minus x is 3x squared minus 1. So So we have that rule. Now we could expand that. Let's see, we have 2x to the fourth, and 2x times negative x would be minus 2x squared. And we expand this, we would have 3x to the fourth, and minus x squared, and plus 3x squared, and a minus 1. If we collect all of our like terms, 2 times x to the fourth plus 3 times x to the fourth is 5x to the fourth. We've got 3x squared. There's negative 3x squared and another 3x squared, so there's no more x squareds. Taking care of those two already. The only thing left is this negative 1. Oh, that's kind of interesting. Now, you might have noticed that I didn't necessarily have to treat this as a product. I could have multiplied it out and had a sum of different things. So another option for finding this derivative would have been to multiply it out before you took the derivative. X squared times x cubed would be x to the fifth. X squared times x would be minus x cubed. 1 times x cubed would be plus x cubed, and 1 times negative x would make negative x. So when we're talking about the derivative of this product, we're really talking about the derivative of this sum of terms. And I notice that the x cubed and the negative x cubed cancel, so we get x to the fifth minus x. And by the difference rule, you can just take the derivative of the first minus the derivative of the second. The derivative of x to the fifth is 5x to the fourth. The derivative of negative x, that's just like part of the line with slope negative 1, right? The derivative must be negative 1. So notice we get the same answer in this case. We multiplied it out and got a bunch of terms and then just used the sum rule, or difference rule, I guess. Here we used it as a product. It doesn't matter which way you do it, you should get the same answer.